This is session 4 of our Intro to Multivariable Calculus, and this week we get to talk about multiple integrals. So, before we do that, we should talk about what single variable calculus integration meant, and then how we can extend this to maybe one or more dimension, because we'll talk first about double integrals and then we'll go on to triple integrals in just a few minutes. So, before we start, let's talk about this definition of the single variable integral. So remember, we would read this integral from a to b, because a to b are our limits, and that's going to happen over, oh, that's really thin, over the x-axis, so something from a to b, like that. And then this whole thing is the limit as n goes to infinity, so number of rectangles goes to infinity. We're summing up all of these things. So let's think about what this looked like. This thing was called the Riemann sum. This is a Riemann sum, which just meant adding up a bunch of rectangles. The rectangles have width given by delta x, or when they get really small, dx. So this delta x stands for the width of one of these rectangles. And we can have uniform width, where all the widths are the same, they're just all delta x all the way across, or they can vary. It doesn't matter actually, because they're going to get so tiny that it really just doesn't affect our answer at all. Now for each rectangle, we choose some function value. This would be our f of x, and this is the y-axis right here. There's our y-axis. So we would choose some function value on the y-axis, f of x, and this represents the height of the rectangle, the height of one of these rectangles. And when we put those things together and we multiply the width by the height, it looks like this, f of x times delta x, and that equals the area of one of the rectangles. Now, since that's only one of the rectangles under the curve and we want to find all of them, we use this guy, which is a sum, and this adds up all of the areas of the rectangles. So it adds up all of the areas, and actually that's why our integral symbol looks a little bit like a stretched out S, because that's really what it's representing, which is a sum. Now, in 2 dimensions, this is all friendly, but we have to think about what this means if we extend this in a third dimension this way. So what if we have x and y, and then we have a third dimension coming out of the paper? And in that case, this is what our Riemann sum would look like. Everything is basically the same, except instead of delta x, we're going to have delta a instead. And delta a just represents the base area of one of these, which is now in 3 dimensions, one of these 3-dimensional prisms. So the base of one of these prisms isn't going to have a length, it's going to have an area, and so we'll call it delta A, or eventually we'll call it dA when it gets really tiny. So everything is the same. We're going to take all these little prisms, infinitely many of them, because we want to be as accurate as possible, and then f of xy times delta A. So, like I said, delta A in this case represents the base area of a prism. Now, these can be regular or irregular, like all the areas can be the same, or they can vary. It really doesn't matter, because they're going to get so tiny anyway that it doesn't affect our answer. F of xy, now, it's still the height of a prism, although now, since we're dealing with a 2-dimensional plane, we need 2 of the variables to be able to find the function value. So this is the height of a prism, and when you put these things together, the base area times the height, so we'll have something that looks like f of x and y, some function value, and that's in the z direction. Like in this case, this would be at a z direction. That's where we're talking about height. F of xy times delta a, height times the base area, this gives a volume of one of the prisms. Volume of one of the prisms. And then of course we don't just want one of them, we want to add them all up, so we sum them. So this adds all of the volumes. Adds all of the volumes. and we use the double integral symbol to show us that we're summing this over 2 dimensions, right? It's a 3-dimensional volume, so our base is a 2-dimensional area. And this R just stands for the region over which we're integrating. So when we had a single integral, we had a length over which we were integrating, so we could say integral from A to B. Now we're going to be integrating over, like in this case, it looks like this entire area, and this would be our region that we're integrating over. So before we actually do an example, one nice thing to point out is all the properties that you already know about integration still apply to double integrals. So for example, if someone puts a constant in front of the function in the integrand, you can pull that out to the front. So this is the same as the constant times this double integral over the region, whatever region we're talking about, of f of x and y dA. This is our little area element. And then you can separate these things. If someone has a sum in an integral, you can separate it into 2 different integrals. So I'm just going to sort of shorthand this plus the integral of g dA. The other thing that you can do, and this is probably less common, but you can still do it, is split up this region into 2 smaller regions. So remember, when you're dealing with single variable calculus, maybe if you're integrating from A to B, it's the same as integrating from A to C, and then again from C to B. It's like you can split this up. You can do the same thing with double integrals. So you could split this into 2 smaller regions, and you'll still get the same volume. Works the same way. So now let's see how to actually evaluate these things. We're going to start only integrating over rectangular regions just because it's so much simpler than integrating over non-rectangular. Well, I don't want to say so much simpler, but it's a lot simpler than integrating over non-rectangular regions, which is going to be the next section of this note packet. But we'll start with these nice friendly rectangular regions, and what that's going to give us is the ability to put in limits on both of our integrals. So if everything is a nice rectangle, we're just going from, x equals 0 to x equals 3, and then y equals 1 to y equals 2, then we have this nice rectangular region and you can just put numbers in here. So we'll start with that. The nice thing is about double and triple integrals, you evaluate them much like you evaluate partial derivatives. So what I mean is you think of one of your variables as a constant and then you trade this off. So looking at this first integral, I see here's the integrand, this 1 plus 8xy, and then I see instead of dA it says dy and then dx. So I'm going to kind of work as we normally do in math from the inside to the outside, and I'm going to evaluate first this integral only with respect to y, and I'm going to treat x as a constant. So meaning like I can pull it out to the front of the integral like it integrates in the same way that a constant would, but for this particular integral I'm treating x just the same way as I would a constant. And then I'm going to get an answer and I'm going to integrate again, that time with respect to x. So let's start with this inside integral. I'm actually just going to write it off to the side here. So the integral from 1 to 2 of 1 plus 8xy dy. So I integrate in exactly the same way as I normally do with respect to y in this case. 1 integrates to y, and then the 8x is a constant, so you can you can basically just like ignore this. The 8x just sort of hangs around, and then we integrate y like normal, so y squared over 2, which simplifies to y plus 4x y squared. And then I'm going to evaluate this where I'm ignoring x for right now, but y is going to go from 1 to 2. So I'm plugging in 2 first. So this is going to become 2 plus 4x times, and then when I plug in 2 for y, not for x, this is going to become a 4. I'm going to take whatever this is when I simplify it, which is 2 plus 16x, and subtract the same quantity when I plug in 1 for y. So 4x. And when I simplify this entire thing, we're going to get 2 plus 16x minus 1 minus 4x. So this should turn into 1 plus 12x. And let me just look at my scratch paper because I messed this up on the first attempt at this video and didn't distribute the negative like a rookie. So, okay, so that's what we should get, 1 plus 12x. Okay. Now, I'm going to take this answer, and that basically goes right here. So now my integral becomes the integral from 0 to 3 of 1 plus 12x. Notice that the y has gone away completely. And I'm back to basically single variable calculus. So I'm just integrating with respect to x, and in the end I'm going to take my limits from 0 to 3. So 1 integrates now to x. Now you have to be a little careful here because on this first line, the integral of 1 was y because we were integrating with respect to y. So you do have to be conscious of like what is your variable here. But in this case, 1 integrates to x, and then 12x integrates to 12 times the quantity x squared over 2, or in other words, 6x squared. So this whole thing becomes x plus 6x squared, and we're going to evaluate from 0 to 3, which, let's see, is going to be 3 plus 6 times 9 is 54. The 0 goes away in all of this, so I'm not even going to write it, and your final answer is 57. And remember, this is a unit of volume. So if this was an actual application problem, maybe it would be something like cubic feet or I don't know, cubic meters or something like that. But this is a volume answer. Now, I just wanted to demonstrate on this first page. You'll notice that these are exactly the same integrand, this 1 plus 8xy and this 1 plus 8xy. The only change that I'm making here is that I've switched the order of the integrals. So now first I'm integrating with respect to x from 0 to 3. These 0 to 3 limits still go with x. And then in the end I'm going to integrate with respect to y. So it would make sense intuitively that we should get the same answer, but let's just see it in action. So I'm going to integrate first from 0 to 3 of 1 plus 8xy, and I'm integrating with respect to x. So I'm just going to treat y as a constant. Now, since I'm integrating with respect to x, 1 integrates to x, and 8xy, well, the 8 and the y are constants, so I'm just going to write those. So 8y, and then x integrates to, as it normally does, x squared over 2. And this simplifies to x plus, what, 4x squared y. When I simplify the whole thing, and I'm going to evaluate this from 0 to 3. When I plug in 3, the 0 is not going to do anything, so I'm not even going to plug it in. But when I plug in 3, I get 3 plus 4 times 9 is 36. So I get that. And now that's my answer, that basically like this takes the place of this entire inside integral. And now I'm going to go back and do the same thing again, except I have a new integrand, and now I'm integrating with respect to y for this outside integral. So this is 3 plus 36y dy. So 3 in this case, since we're integrating with respect to y, integrates to 3y, and 36y integrates to 36y squared over 2, or in other words, 18y squared. So I've got 3y, equals, not plus, equals 3y plus 18y squared, and I'm going to evaluate from 1 to 2. That's a 2. So when I plug in 2 into this first quantity, I'm going to get 6 plus, what is 18 times 4? 72? Yeah. So 6 plus 72 minus, and then I'm going to plug in 1, which just gives me 3 plus 18. So in total, 6 and 72 give me 78, and I'm going to subtract 21 from this entire thing, and not surprisingly, we're ending up with the same answer of 57 units of volume, because it would make sense if we're integrating over a rectangle, we didn't change anything except for the order, we should get the same answer on these two things. So the other way that I can phrase this question is, instead of giving you the limits, I can tell you integrate over this region, and then I can describe the region like this. So R is the set of all the points such that, you read this little guy as such that, you've seen something like this before probably, such that x is between -3 and 2 and y is between 0 and 1. So I don't know if this looks scary to you at all, but just in case, if we were to draw this, it's saying x is between -3 and 2. So x goes between -3 and 2. So like this creates this like vertical band of space on the x-axis, and our region is anywhere in there so far. X is anywhere between 0 and, or between -3 and 2. And then y goes from 0 to 1, so that creates a horizontal band on the plane, which gives us this region that meets both the criteria, and of course the shape of this region is a rectangle. So there's really no difference in describing it this way than what we were just doing with the limits. So I'm going to do it in the exact same way. I guess the only difference is this does not define an order. It doesn't say first integrate with respect to x and then integrate with respect to y, or vice versa. But those examples that we just did kind of show you that I don't have to define an order because it doesn't matter anyway. So I'm going to, let's see, I'm looking at this and thinking about integrating first with respect to y and how this is going to become a y cubed, and I don't want to do that. It doesn't matter, but I just don't feel like doing that, so I'm going to integrate first with respect to x. So I'm going to make my first integral go from -3 to +2. This is going to be y squared x, and I'm going to integrate first with respect to x. And then when I'm done with that, I'm going to take my second integral from 0 to 1 with respect to y. And I'm going to do it exactly the same way as the above example. So when I'm integrating with respect to x, anything with y, but in this case y squared, is a constant. So it really doesn't matter. I'm going to say the integral from -3 to 2 of y squared x dx actually is the same as y squared times the integral from -3 to 2, because if it's a constant, I can pull it out to the front. I'm pulling that y squared out to the front. So this is y squared times x squared over 2, evaluated from -3 to +2, which is what? When I plug in 2, this becomes 4, but over 2, so I get 2y squared to start out with, minus, and then when I plug in -3, this is a 9, so 9 over 2 times y squared, so minus 9/2 y squared. So I think altogether, this part is the same as 4/2 y squared minus 9/2 y squared. So I think my very first part of this integral turns into -5/2 y squared. And I'm going to take this quantity and plug it back in where this inside integral was, and then do this all again, but this time with respect to y. So let's just finish this one up. I'm integrating from 0 to 1 of -5/2 y squared dy. I'm going to pull out the -5/2 because it really is a constant, or if it was anything with an x, I could do that as well. Y squared dy. And then this is -5/2 y cubed over 3 from 0 to 1. The 0 doesn't do anything, so I think this entire thing is going to turn into -5/6 for our volume. And I am checking my scratch paper, and that is exactly what I got earlier. So -5/6, which might make you think about like the signed area that we know about single variable calculus. One thing that we know is that when you have area that goes below the x-axis, this counts as negative area. So very, very much the same thing when you are dealing with three-dimensional volume, when you have, it's a little bit hard to draw this, but when you have a volume that's like down below the z-axis like this, this would count as negative volume. So at least some part of this solid lies below, I shouldn't say z-axis, what I mean is the xy plane. So in the negative z area. And some of this must, because we got a negative answer. Now at this point, you can either continue on to the next section, which is talking about how to take a double integral over a non-rectangular region, or you are ready for exercises 1, 2, 3 without calculators, and 4. Now 4 is the only one where I sort of defined the rectangle in these terms. You can integrate with respect to x or to y first, it doesn't matter, you'll get the same answer anyway. All the rest of them are just sort of standard, like the first two examples where I define the order for you. So first integrate with respect to x and then y. First integrate with respect to y and then x. So you're ready for exercises 1 through 4, or you can continue on to the next video, which is about integrating over non-rectangular regions.